This video is about side chain oxidation, specifically aromatic side chain oxidation with alkyl groups on an aromatic ring. The hydrogens at the benzylic position, which are the ones right next to the ring that I have drawn in, can be oxidized to give with potassium permanganate to give the carboxylic acid. And when I say the hydrogens are oxidized, really what I mean is the whole side chain is oxidized. So if it was a methyl group, it's oxidized to benzoic acid. If it was an ethyl or a propyl group, like what is shown here, it's oxidized to benzoic acid. The carbons that are on the end of the chain farther out than the first carbon next to the ring are all oxidized away and probably get oxidized to like acetic or formic acid. So in order for this reaction to happen, you have to have hydrogens on the benzylic carbon. So this next structure that is shown has two different kinds of alkyl substituents. One has a benzylic hydrogen on its carbon next to the ring, and the other one is a T-butyl group. Only the one that has the hydrogen on the benzylic carbon is oxidized in this reaction. The T-butyl group is left alone. So I have labeled the carbon with purple, which is the color of potassium permanganate, that gets oxidized, and the one with red that does not get oxidized because it does not have any benzylic hydrogens. Here is another feature of side chain oxidation that is really useful to us at this point in this course. The R group of methyl, ethyl, propyl, T-butyl, whatever, those alkyl groups are orthoparadirectors. If you have the oxidation to give carboxylic acid, the carboxylic acid substituent is a metadirector. So depending on when you carry out the oxidation in a multi-step synthesis, you can influence the reactivity of the ring and determine whether incoming substituents would go orthopara to the propyl group or whether they would go meta to the carboxylic acid group, which can be kind of handy.